Now we look at the general channel model that includes the Doppler effect. So in this case, we have again a time varying attenuation, time varying phase shift, and time varying delay, because the mobile station or the setting is mobile. So the distance changes, the delay changes, hence the phase shift changes and the attenuation changes. Again, the number of paths, the path of the multipath is also a function of time, so it's a variable. This form is a linear time varying system, in contrast to what we are used to, which is linear time invariant system. This means that this system is linear, but it changes with time. Okay, now to describe the system, we need to address it statistically. So we compute the autocorrelation function with this of this impulse response, or this system function. Now, as you can see, we have a function with 4 variables: t1, t2, tau1, and tau2. It's too complicated, so we need to assume some simplifying assumptions or conditions. The first one, which is we are used to it, which is Whiteson stationary, meaning the autocorrelation depends on the difference in time, not the actual time instance, so we can simplify t1 and t2. Another simplifying assumption is the uncorrelated scattering, meaning that the multipaths are uncorrelated, so the time delay tau1 is uncorrelated, does not depend on tau2. Okay, in this case we can simplify this 4 variable function into 2 variable functions, tau and delta t. Okay, now we can look at this function, which is known as the scattering function in the Fourier transform. So in the Fourier domain or the frequency domain, so we take the Fourier transform of it, and again we get a 2-dimensional function, which is again a bit too complicated. To simplify matters, let us say that we want to look at it in a single time instant. So we set delta t to 0 and we get this function. This function is called power delay profile. So it gives us the power of the system as a function of the delay, right? And as stated here, it represents the correlation of the average power for different delays. Okay, and this function has a special form. It's monotonically decreasing, so it's always decreasing with tau, which makes sense, right? Because as the delay increases, meaning that we are moving away from the transmitter, the power should decrease as well. Okay, so we can make a PDF out of the power delay profile by normalizing it. Now since this is a probability density function, we can compute the mean and the standard deviation or variance. Now this is called the mean of the delay spread and the root mean square of the delay spread. Okay, now we want to find a value for tau, okay, such that the delay profile or power delay profile is approximately 0 or negligible. This is very useful to us. Okay, in this case this means that the symbol duration is much smaller than the root mean square delay of the spread, which is in this form, right? So it's much smaller than. In this case, the multipath components are correlated, meaning that they have similar delays, meaning that the received symbols are unresolvable, meaning that they are stacked above each other, leading to narrowband fading or no ISI. So this is no ISI, which is equivalent to having narrowband fading. So if the symbol period is much smaller than the delay spread, this means that we have a narrowband fading or we have no ISI. Okay, so how much small? So it depends actually on the reference or on the textbook. Usually 10 times the delay spread is good. So if TS symbol duration is less than 10 times the delay spread sigma Tm, we have no ISI. Otherwise we assume that we have ISI. Okay, this is in the time domain. Let's look at it in the frequency domain. So if we take the Fourier transform for the PDP, we get this function. Okay, from this function we can compute the coherence bandwidth, which is actually the inverse of the delay spread. We want to find a value, okay, it's called the coherence bandwidth, such that the autocorrelation or the correlation of the power in the frequency domain is negligible. Okay, so this is called the coherence bandwidth. Right, now if the signals or the pulse bandwidth is much smaller than the coherence bandwidth, this means that we have similar frequency powers, right? Meaning that they have high correlation. Consequently, we have flat fading or again narrowband fading. Otherwise, we have frequency selective fading, right? Now a simple form of the PDP for the delay profile is the exponential one. It's monotonically decreasing, of course. Okay, this form is very simple. Why? Because we can find the mean and the standard deviation, which are equal to each other and equal to the delay spread. And its Fourier transform has again a simple form. Let's take an example. Now consider an indoor channel with a sigma Tm equal to 50 nanosecond and outdoor channel with 30 microseconds. So this is much larger than the previous one. So the outdoor channel has a sigma that is much larger than the indoor channel, which makes sense, right? Find the maximum data rate for both channels, meaning this means that we want to find the bandwidth. So we don't have ISI, we don't have intercept interference. Okay, for the indoor channel we need to find 10 times the sigma, which is 500 nanoseconds. So we say that if the symbol time is much smaller than 10 times the delay spread, this value, meaning that we have frequency selective fading. Otherwise, if it's greater than this value, we have flat fading or no ISI or no frequency selective fading, right? So this means that we have 2 megabit per second in the indoor case. For the outdoor case, it is 3.3 kilobit per second, which is very small.